Hi, Liana, how are you?
Hello.
Hello, hear me?
Yeah.
Okay, are you okay so far?
Yeah.
Did you see the lecture file screen now?
Yeah.
Okay. So far, how is your class going in your school?
It's good. We're having a test tomorrow.
Oh, so which chapter they are testing now?
It's unit 6.
Unit 6, what?
The internet.
Internet.
Yeah, like internet hardware and like IP addresses and like DNS and like cybersecurity.
Well, okay, internet. Let's do this. So this is a programming I can teach you some other time. Let's jump to the internet. Is that okay?
Yeah.
Originally, we are go to the unit 3 to teach you on the programming and algorithm, but this one we want it to be continued. And since your school have different things, so this 5, 6, 7, 8, these are programming. We will at this moment just skip. So we'll go to the unit 4 in our system, and I will jump to this lecture 10 internet for you. Okay, let's go. It's better for you, right? Okay, let's go to this one. The unit number may be different, but I think the material is would be similar. So first one, we will talk about internet. Okay, we'll talk about internet today. We may need to know about the the previous chapter on computer. Okay, so let's actually go briefly through the computer, and then we'll go to the internet. Okay. So first thing is that you need to know about what is a computer. So a computer is a device to do computing. So you do have an input and you do process it and you get an output. Okay, that's a computer. And then your computing device, you do have a lot of input device, mouse, keyboard, and then touchpad, these kind of things. These are different input. And there are also some outputs. Speaker, headset, these are output. Printer, these are output. So you do have some inputs and output, and then these are computers. And nowadays, not only computer, it may go to the robots. Okay, it may go to the robots. Okay, I am not trying to teach you the whole thing for hardware now. I'm just giving you the idea of what is internet and computer. So a computer, you do have some input and output. So one of the input and output is the communication channel. So your computer may go through communication channel and then go to internet, and then you receive data back to your computer. Okay, so there's something that net connected to your PC and also connected to internet. So it goes through the internet goes through the I/O system, your I/O input and output unit, and one of them is an internet card. Wi-Fi card. Okay, one of them is Wi-Fi card, and you go through there. So the I/O, your system, you do have a CPU, RAM, ROM, and then I/O. I/O is connecting to your like Ethernet card, USB card. Okay, those kind of card being connected to I/O, and CPU is your computing device. So when your hard disk can read some data through I/O channel and go to your RAM, okay, and your CPU get the data to process. Okay, that's about it. That's the part that I want to cover for computer part. Let's go to the internet now. So one computer is a computer. You do have input and output. So now first one is what is network? So we talk about a computer. A computer is a single box that to do computing. So that here we do have a computer. Okay, we do have a computer. Now, Liana, what is a network?
Um, It's like two or more computer systems linked together.
Yes, two or more computers connected together. So here let's actually do this, and these three computer connected to a device, and this device we can call it a switch. Okay, we can call it a switch. Okay, we call it a switch. So switch means that your computer may go from this computer to this computer, or may go from this computer to this computer, may go from this computer to this computer. So there's a switch among them to routing the data from one computer to the other. Okay. And then next one is the router. Okay, this one is called router. Okay, sometimes it's also called gateway. So this gateway is that you do have gateway and then you do have Wi-Fi. You do have Wi-Fi. And through Wi-Fi, this gateway or through internet, you may connect to the internet, or you may go through the Wi-Fi using wireless to communicate with another computer. So everybody's data, if you want to go to internet or download from internet, then you will go to here and go to the internet. Okay, so this one we call it router. And then output of the router, you go to where? Go to AT&T or go to Verizon. This one we call ISP, Internet Service Provider. So this internet service provider can be AT&T, or Verizon. Is that okay so far?
Yeah.
So far up to here is inside one building. This is inside one building. Inside one building, you have Wi-Fi, you have a router, you have a few computers connecting together. This is inside one building. And then you go out of building, you get to the outside. You may go to the outside, and then that will go to the internet service provider, like such as AT&T, and AT&T bring your data to the whole internet. Okay, AT&T bring your data to the whole internet. Okay, now I'm going to copy this one and put it in the group. Okay, so later you can take notes. Okay, so this one is network. A network is a connection among two or more computers called network. And then let's see. So that's actually a network. So you do have a building. Okay, let's assume here is a building. And then inside the building, you do have a gateway. Okay, you do have a gateway. And then with the gateway, you do have some Wi-Fi here. But you may have two floors, first floor, second floor. So this Wi-Fi connected to a few computer upstairs and maybe some computer downstairs. And everybody has a local internet. So this local internet, we call it local internet, local network. We also call it LAN, LAN. Okay, so this one is a LAN. So this LAN connecting together, and then next one is you will be connected to through here to AT&T or some. Let's put it this one called Internet Service Provider. So this one can be AT&T, okay, and then or Verizon, okay, or maybe Comcast. Okay, it's a different company, but you do go to this ISP first, and then this ISP will go through some router. Let's assume that actually right now you are in let's assume you are in Fremont. Okay, so this one, let's assume right now we are in Fremont. Okay, base station. And then you may need to connect it to some other location. Okay, so these some other location would be right here. You may connect it to first step. This one maybe is Berkeley. Okay, let's assume this is Berkeley. So Berkeley connected to Utah, University of Utah. Okay, the University of Utah. So it connected to University of Utah. Okay, let's put AUT. Okay, so it's connected together. And the University of Utah may connect to NYU. Okay, let's assume here is NYU. And then NYU connected to another router. And then let's assume that somebody living actually in New York, they also have their ISP, their AT&T, okay, or their Verizon. Okay, and then this one connected to a building. Okay, and inside this building, we do have inside this building, we do have a few computers. We do have also have a gateway. We also have a gateway. We have a gateway. We also have a gateway right here. We also have a few computers. Okay, one of the computer is used by a person called Bob. So basically, this is the whole network. You come from your Fremont home, connected to another person whose name is Bob in New York. So you go to your LAN and then go to your ISP and go to the this several computer. We call it each of these computer. We call it a router. Router is to help you to find a route. Finding a route for you. Okay, so this router can be at the Berkeley, can be at the Utah, can be the anyway. These different router, depending on where your data will go to, okay, or where you want to send the email to, we really don't know which router it will be. Okay, at the runtime, they'll determine which router it should be. Okay, is okay so far?
Yeah.
And then eventually it will arrive at Bob's local ISP. And then Bob will be connected to Wi-Fi and then get the data from ISP and then get the data that you send. Okay, these are the whole process of the things. So now right here, you do have one LAN right here, one network right here. Here you do have another network. And then inside Berkeley, they may have many network, many buildings. Each building has a network. Utah also had many network. Okay, so now the term internet. The term internet. So what is internet?
Like a bunch of, it's like a network of networks.
Yes, it's called network of networks. What do we mean network of the network? So right here you do have a network in a building. And then here you have a network in a building inside Berkeley. Here you have the network inside the building of the Utah. So all of these different networks being connected together, they form a big network. That bigger network is called internet. It's a network among the network. Is that okay? It's a network of the network. Is that okay so far?
Yeah.
Okay, that's the internet. Okay. Now next one. Next one is what is web?
Mm,
What is web? We say website, but what is web? Do you remember? No? If you don't remember, it's okay. Just let me know.
I I don't know what the web is. I just know websites.
You know website, but you don't know what's web. Okay, it's okay. So when you look at the spider spinning web, right? So spider's web is like this. Something connected by a lot of wire or a lot of line and forming a connection, we call it a web. Okay, so originally the idea is from a spider's web. And then when we look at the internet, we do have a lot of computer connected together to a network. Okay, so we do have computer connected to the network. So we do have a computer like this. This one connected with this. This one connected, three of them connected together. So this is three connected together, and then this three go to a router, and this router get out to ISP, and then ISP, there are many base stations of the ISP. They're connected together. And then this connector connected to another router, and then this router connected to three computers right here. Okay, so basically, the bigger connection of different network getting bigger. At any time, it's just like spider. You can connect more layer of line there, and then getting bigger. So the internet connection is very similar to the web the spider is building. Is that okay?
Yeah.
Okay, so you actually can plug your computer to the network, and then the network will accept your computer and then become part of the network. And then some other people may unplug his computer, and the computer will get out. So this network is actually in and out at any second. A lot of computer come in, a lot of computer get out, a lot of computers shut down, a lot of computer just started. Okay, and the network keep getting bigger, getting smaller, getting bigger, getting smaller, getting bigger, getting smaller. Okay, that's a whole web. Now, then we know that actually that is web. Now next word is, what is World Wide Web? Or we call it WWW.
Like a public
Hmm?
like a public internet system where like the content can be shared over the internet.
Okay, so web is a network. Your local network, we call it a web. So World Wide Web is the structure or protocol that can accept any network and connect them together for the whole world. The whole world will be connected using the World Wide Web connector. The whole world will be connected by World Wide Web. It's a web structure that can be accepted worldwide. Is that okay?
Yeah.
So at this time, your computer, actually, you can plug in your computer right here. And then you get onto the internet right away. And some other time you may close your computer and then you will get out right away. So at any time you can insert or delete a computer on the internet. And this internet, it will be operating just normal. Nobody will be hurt. Then we call this whole structure a World Wide Web. It's a worldwide web, worldwide networking. Okay, this is the so-called World Wide Web. Now we have some know about the terminology. Let's actually continue. Okay, so that's the part that we want to get started first, knowing about what is a network, what is World Wide Web, okay? So now we want to know about more about network. So network, first thing before we go into deeper, you need to know about there are 7-layer architectures. Okay, you need to know about what is the 7-layer architectures. Okay, I think right here, this one is a little bit too hard now. Let's go back to the chapter 9 material. Let's go back to the computer part. Let me move down more. Okay, right here. So the first thing that you need to know about is the 7-layer architecture for the internet. Okay, about network. So you first need to know about what is HTML, what is HTTP, what is ASCII, what is protocol. And what is abstraction. First one is, what is protocol? Okay, here we do have some words. So what's in your mind, what is protocol? What that it means by protocol?
It's like agreed upon rules that standardize communication.
Yeah, so basically it's a standard. Why we need standards? Why internet we need standards?
Because then discussion would be difficult without it.
Why difficult if we don't have standards?
Then like
If you don't have standard, you cannot communicate. For example, if you speak Spanish to me, I don't know about Spanish, then how can we communicate in Spanish?
yeah.
So before we two people communicate, I need to talk about what language we talk about. So you need to, at this moment, we are using English. So maybe you are able to use Chinese. So we may be able to use Chinese to talk. But that's not enough. Sometimes some people may use Spanish. But for us, Spanish is not a language that we can use. At least I don't know about Spanish. Even you may know, but I don't know. So then that's not a standard that acceptable to me. So protocol is a set of rules that actually governing exchange or the transmission of the data among the devices. So when two devices want to talk, they need to know about each other's standard. right? You know what I'm saying?
Yeah.
So they can talk to each other. That's one thing. Two people want to talk, they need to have a standard. Second, when the company who sell the Wi-Fi or who sell the computer or who sell the ISP service, they also follow the same standard. If they don't follow the same standard, then you buy one computer, IBM computer, and I buy a HP computer, but HP computer doesn't talk to IBM computer, then we are in big trouble. Does that make sense? Hello, does that make sense?
Yeah.
So standard is set up for communication. So standard is set up for communication for it may for the vendors or it may for the for the people who use the internet. Okay. So one question: who set up the internet standards? Who set up the internet standard for people to follow? Who? Who designed the standard and you need to follow the standard? Who set up the standard? You, me, or who? This may be tested tomorrow. You need to know about who set up the standard for the internet so everybody can follow. Government? Yes or no? Is the communication standard set up by government?
No.
Then who? So MIT, universities? Yes or no?
No.
Then who? Who set up the standard for everybody?
Well, I don't know who it is.
You don't know who? You don't know, that's okay. The answer is everyone or no one. Okay? The answer is no one or everyone. Sound like I'm not talking about anything, but in fact it's everyone. So let's actually look at here, code.org. Internet is for everyone. Okay, let's look at this internet. Can you hear it?
What is the internet?
Yeah.
The internet is like a popular thing.
Some satellites up there.
I picture in my head with like waves of internet going to the phone.
Somebody told me a cloud once. The internet is a lot like plumbing. It's always moving.
Most people don't have any idea where the internet came from, and it doesn't matter. They don't need to. It's sort of like asking who invented the ballpoint pen or the flush toilet or, the zipper. These are all things we just use every day, and we don't even think about the fact that one day somebody invented them. So the internet is just like that. Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. It was a result of another experiment called the ARPANET, which stood for Advanced Research Projects Agency. Now,
okay, the initially is called a ARPANET. ARPA is the Advanced Research Project Agent. ARPA. So ARPA is a organization for defense department. So later they also have something called DARPA. So ARPA or DARPA is a research agent for the Department of Defense. So originally when they set up this network is for only 23 university and some research organization and naval office, something like that. So initially this network is very small and they do experimental work and then they set up the ARPANET. So starting from ARPANET, the first network, internet start to grow.
It was a Defense Department research project. Paul Barron was trying to figure out how to build a communication system that might actually survive a nuclear attack. So he had this idea of breaking messages up into blocks and sending them as fast as possible in every possible direction through the mesh network. So we built what eventually became a nationwide experimental packet network, and it worked. Is anybody in charge of the internet?
Elves, obviously elves. The people who control the Wi-Fi, because no Wi-Fi, no internet. T-Mobile, Xfinity, Bill Gates. Right?
The honest answer is, well, nobody, and maybe another answer is everybody. The real answer is that the internet is made up of an incredibly large number of independently operated networks. What's interesting about the system is that it's fully distributed. There's no central control that's deciding how packets are routed or.
Okay, so internet grow, like you have many ISP, many company, and then many university, many governments. They all connected together to an internet. But who in charge of this internet? Nobody. Nobody in charge. Or you can say everybody. Who invented this internet? I'm sorry. Who actually set up the standard for the internet? There's also nobody or everybody. Okay. So this answer both are very vague. I'll talk about who set up the standard later. But right now, at this moment, you know the internet is for everyone, designed by everyone, and owned by everyone. And then there is no government or company who is actually controlling the internet right now. Okay, nobody, absolutely nobody. No one, even the government of the United States won't control it. Okay.
Where pieces of network are built, or even who interconnects with whom. These are all business decisions that are made independently by the operators. They are all motivated to assure that there is end-to-end connectivity of every part of the network, because the utility of the net is that any device can communicate with any other device, just like you want to be able to make phone calls to any other telephone in the world. There's nothing like this that has ever been built before. The idea that what you know might be useful to somebody else or vice versa is a very powerful motivator for sharing information. By the way, that's how science gets done. People share information. So this is an opportunity for people to think up new applications, maybe program them as apps on a mobile phone, maybe become part of the continued growth of the infrastructure of the network to bring it to people who don't have access to it yet, or just make use of it on a day-to-day basis. You can't escape from contact with the internet. So why not get to know it and use it?
Okay, so number one, internet is for everyone, built by everyone, owned by everyone. Okay, and then internet, we want everybody to have access to. Okay, and then internet, but we do need protocol. We do need a standard to talk. Otherwise, we don't know about each other. Now, who make the standard so everyone can work on and can actually participate to make the standard. Even you or me can volunteer to work on the standard. But in fact, there is a committee called Internet Engineering Task Force. It's called IETF. Okay, so this IETF organization, Internet Engineering Task Force, this organization is in charge of all of the internet standard. So, for example, somebody may want to actually set up a new standard. Who will approve it? This IETF will approve it. But who will design the new standard? Basically, you can design the standard. I can design the standard. Everyone can design the standard. And then once we design the standard, you can actually submit to IETF and say, oh, Mr. Chairman, me invented a new standard. I want this standard to be used by everyone. Can I have this one submitted to your website and then let's discuss whether it will become a new standard or not? Okay, so they will from time to time, this IETF committee will have a sub meeting, and then they will determine which standard will be taken, with which standard will not be taken. Is that okay so far?
Yeah.
So IETF is making the standard for everyone. But who can participate IETF? Everybody, like you, me, everybody can participate. You can volunteer for the IETF. So here, if you want to volunteer, you can search internet. Volunteer for IETF. Okay, so here we do have tech volunteer needed. Okay, I'm sorry. They do have some volunteer for IETF. You can go for participate in IETF. Okay, so if you want, you can volunteer to participate IETF. Okay, so get it started, and then you making internet drafts, and then you want somebody to actually look at your job and approve it, and you may participate IETF hackathon to invent new things. Okay, so there are many things with IETF going on. And this IETF is the organization who approve or disapprove the internet standards. Okay, so in a way, nobody define the network. Nobody or everybody. We don't have clear definition. And then it's not even government, not Microsoft, not Bill Gates. It's everyone who collectively to define the internet. And the internet standard is approved by the IETF. Okay. Now, the existing standard, we call it 7-layer architecture. So 7-layer architecture is laid out like this. This is 7-layer architecture. You need to memorize them for these different 7-layer architecture. So on the top, you do have application layer. So application layer is your HTTP, your HTML, your email, those kind of things, your file transfer protocol, FTF. Okay, your email also in the layer 7. So layer 7 is application layer. Application means software. So layer 7 is software layer. Is that okay?
Yeah.
Layer 6 is called presentation layer. So layer 6 presentation layer is in charge of JPEG data representation. So encoding, decoding, compression, decompression is under the software, and it's layer 6. Is that okay?
Yeah.
Now, next one is layer 5. Layer 5 is the layer under the compression. It's called session layer. So session layer in charge of setting up the communication. So let's assume that I'm logging into the Citibank. Okay, let me log into the Citibank. So Citibank is right here. So now we actually right here, you actually type in my password and keyword, everything, and then it will go into the Citibank account. Okay, so it go to my Citibank account. So anyway, starting from here, I can actually look at my bank account content. So that's actually is my computer. It actually is my computer right here. Go to ISP and go to internet and then go to everything, other things, and then go to Citibank. So basically, I transmit my password and everything to Citibank. Citibank approve and send back a web page. So we do communication in between. Okay, but I may sign off. So starting from my login to my sign off, this whole thing we call it one session. Is that okay?
Yeah.
So one session means that right now I am talking to you using Zoom. So for the 1.5 hour that we are talking, we are in one session. Is that okay?
Yeah.
Or you may use a cell phone to call your mom for 2 minutes, and that 2 minutes is one session. Is that okay? So I use this Citibank, but if I am idle for a few minutes, then Citibank may kick out my login. Then I lost that session, and then I need to log in again. I need to start a new session because the previous session I'm idle for too long, and then I lost it. Is that okay?
Yeah.
So to control who will go to the internet to go to from Citibank to my website, it's called layer 5 session control. So session 5 is in charge of the handshaking of one website to the other, you and me, and then me and the Citibank. Those communication session, whether we are on talking to each other or we are not, or you idle for too long, it's controlled by layer 5. Is okay?
Yeah.
Now, let's assume that I'm talking to YouTube. And so YouTube today we do have a Super Bowl. So I want to do video streaming to from the YouTube. So I need to set up one session. I log in from my YouTube account, and then I set up one session and start to download. Okay, but the file that actually in YouTube is so big that I cannot transmit the whole file at one package to my local. So it actually chopped down to the smaller package. So that's assume that each 1K data is a package, and then it's sent through the internet to my website, to my computer, and then the second one, and then the third one. So there are many packages being sent to my local. So to chop down those packages to a smaller size, it is in this layer 4 transport layer. Is that okay so far?
Yeah.
So layer 5641, 567, 7654. This support layer is in the same computer in YouTube, including the software encoding, decoding, session control, and the chop down of the big file to the smaller one. Okay, these are in one computer. It may be on my computer or maybe on YouTube's computer. Okay, anyway. Next one, you go down to layer 3. Layer 3 is a network layer. So what is a network layer? Network layer is like, okay, network layer is like your computer, you use a browser do encoding, set up a session, chop down the file to a smaller one. So you go in, actually your data goes through your ISP. And then the first one go to Berkeley. So Berkeley is a network. Your local network, you have the network. Wi-Fi has a network. And then Berkeley go to Utah. Utah is the one of the intermediate network. And then you go to the New York City to Bob. So New York City's ISP has another network. So your data hopping through several networks until you go to the internet. So this layer 3 is called the so-called network layer. Is that okay?
Yeah.
So network layer determine where your data will go. So it's just like sending you a mail. The first step is your home. Second step, you will send to Berkeley. Third step, you send the data to Utah. And then fourth step, send to New York for Bob. Okay? So your data hopping from one node to the other, we call it network layer. Okay, so from network layer, you go down to the next layer called data link layer. Data link layer is board layer. What do I mean by network? So you have a computer. Your computer have the Wi-Fi board. The Wi-Fi board talk to the Wi-Fi board of the router. The routers talk to the Wi-Fi board, the internet board of the ISP. So you do have board-to-board communication. Board-to-board communication. This board-to-board communication is in the layer 2. Okay? And then the next layer is called physical layer. So physical layer is in charge of physical signaling. So your data is going through the radio frequency signal and is a sine wave to send out your data. So your wave like that, you send out. So this is 7-layer architecture you need to know. Okay, you need to know. So far, any question?
No.
Okay, I just give you the basic idea of what 7-layer architecture is. Next one, you need to know about the word LAN. LAN is local area network. So your Wi-Fi is a LAN. LAN is local, it's inside one building. We call it a LAN. Okay, next one, media. Media, you have a fiber channel. So this is a fiber channel. You may have a coaxial cable that's actually using copper wire. Okay, using copper wire. You may have the Wi-Fi, it's using radio frequency. Okay. So these are different media. And nowadays you have another one called 5G. So 5G. So what is the difference between 5G and Wi-Fi? Do you know? Sometimes you stay in McDonald's, they do have Wi-Fi, but you don't, if you don't have the Wi-Fi, your cell phone cannot be connected. But if you work,
5G is cellular.
yeah, 5G is cellular. What is cellular?
It's like
What is Wi-Fi? What is cellular? Cellular is your cell phone standard. So you do have a base station. About every 2 miles, there's a station. And then this station connected together. And because they usually line up in the hexagonal area, so each one of these covering certain area. Each one of these covers certain area, and they in the hexagonal shape. So it's actually hexagonal shape. So it look like the cell, look like the cell of the bees. Is okay?
yeah.
That's why you call cellular network. And cellular network is used for the cell phone. So your cell phone talk with each other in 5G, 5th generation cell phone standard. While Wi-Fi is not, Wi-Fi do not have the cellular structure. Wi-Fi, you go to AT&T, and AT&T using cable to ship your data. So usually Wi-Fi is only available inside a building. When you get outside the building, you have to use a 5G, you have to use a cellular. So Wi-Fi's bandwidth is wider, you can download more data using Wi-Fi. 5G actually is less, capacity is smaller. Is okay so far? Okay, so that's the difference between 5G and Wi-Fi, okay? Okay, I don't want to go to the typical part. So first thing you need to know about what is standard. So standard is a set of rule that actually governing the communication. Okay, that's called standard. And we do need standard because if you don't have standard, you cannot talk to each other. Okay. Okay, so protocol is how you communicate. Okay, so here, okay. So HTML is also a standard because we want to design the web page everybody can understand. So you need to have one language to set up the standard, and the language is the HTML. It's a language of the web, okay? This is layer 7 standard. And when they transmit data, they are using the HTTP, so we call it hypertext transfer standard. Okay, it's transfer protocol for HTTP. And ASCII is a coding standard. So ASCII is a data set, is a character set. So when you send out the data through internet, you have to follow the ASCII symbols. Otherwise, the other side don't accept your words. Okay, this is ASCII. So these are different layer 7 protocol: file transfer protocol, hypertext transfer protocol, okay, hypertext SMTP protocol, small emails transfer protocol, POP3 protocol, post office protocol. This is also for email. And then this one is DNS. Now, what is DNS? Domain name subsystem. DNS, what is DNS?
It like translates the names of domains into IP addresses.
Why we need that? So first thing is that you need to know what is DNS. DNS is a, say, www.yahoo.com. This one translates to 32.45.2110.7. A set of 4 numbers is called IP address. Okay, so this to find the IP address for you. So now, first thing is that why we need IP address? Why we need DNS?
To like locate, like for computers to locate each other.
Why you can locate each other by using the IP address? So first is, what is IP address?
Just something that translates names of domains into IP addresses.
No, IP address is just an address. So basically, when you call a cell phone, my phone number is 510-304-9428. So it's a 10-digit number, right? Is that okay?
Yeah.
3 digits for area, 7 digits for my phone, right? So this actually is my phone number. So can you write this? Can you call a number like this? 5555-2222, and you try to call this. Can this be called? Of course not, because it's not following the 10-digit standard for US. Maybe some other country use this 4-4 standard, but in US there's no such 4-4 standard. So phone number is an address, email address, echel@gmail.com. That's its address. Same thing, IP address is also a address. So IP address is the address used in internet. Is okay?
Yeah.
So this DNS is like a translation. So it's just like your www.yahoo.com translate to the real IP address 32.17.212.7. So this one a little bit like post office number. You send the email by post office, so post office 1 mapping to this. While this post office number 1, it may have a real address, a physical address of 38712, and then that's these 3. So that is the domain name. Domain name is the human-like address. And then it will be translated to your post office address that we call it IP address. Is okay?
Yeah.
To find where the number is, we call it the DNS. Where the number is, we call it the DNS. Okay, let's actually look at the code.out video. Okay, let's look at internet address and DNS.
Hi, my name is Paula, and I am a software engineer at Microsoft. Let's talk about how the internet works. My job relies on networks being able to talk with one another. But back in the 1970s, there was no standard method for this. It took the work of Vint Cerf and Bob Kahn to invent the Internet Working Protocol to make communication possible. This invention laid the groundwork for what we now call the Internet.
The internet is a network of networks. It links billions of devices together all around the globe. So maybe you're connected with a laptop or a phone through Wi-Fi, but then that Wi-Fi connection connects to an internet service provider or ISP, and that ISP connects you to billions and billions of devices around the world through hundreds of thousands of networks that are all interconnected. One thing that most people do not appreciate is that the internet is really a design philosophy and an architecture expressed in a set of protocols. A protocol is a well-known set of rules and standards that if all parties agree to use it, will allow them to communicate without trouble. How the internet actually physically works is less important than the fact that this design philosophy has allowed the internet to adapt and absorb new communication technologies. This is because in order
the important part is that this internet technology is designed to adapt and absorb new communication technology. What does this mean? This means that if you are new to the internet and you plug in your computer and you follow the standard, and your computer will be hooked up right away. You will be assigned with a new IP address, and then you will be on the internet nowadays again. So now if 2 years later, some people invented an iPhone 200, a very, very new technology, and then they follow the same standard, and then that iPhone can also be put onto the internet right away. So the current IP address system is designed to adapt and absorb new communication technology. That means that more devices, more different new devices, more computers, more new computers, more new network can all be put into the current IP address domain, and then they will talk to each other right away. Is that okay?
Yeah.
So that just means that your internet is plug and play. They want you to really do plug and play for internet. Okay, that's the design philosophy behind the internet.
new technology to use the internet in some fashion. It just needs to know which protocols to work with. all the different devices on the internet have unique addresses. An address on the internet is just a number, similar to a phone number or a sort of street address that's unique to each computer or device at the edge of the network. This is similar to how most homes and businesses have a mailing address. You don't need to know a person to send them a letter in the mail, but you do need to know their address and how to write the address properly so the letter can be carried by the mail system to its destination. The addressing system for computers on the internet is similar, and it forms part of one of the most important protocols used in internet communication, simply called the Internet Protocol, or IP. A computer's address then is called its IP address. Visiting a website is really just your computer asking another computer for information. Your computer sends a message to the other computer's IP address, and it also sends along its origin address so the other computer knows where to send its response.
You may have seen an IP address. It's just a bunch of numbers. These numbers are organized in a hierarchy. Just like a home address has a country, a city, a street, and a house number, an IP address has many parts. Just like all digital data, each of these numbers is represented in bits. Traditional IP addresses are 32 bits long.
Okay, so traditional IP address, we call it IP4. IPv4 version 4, IPv4. IPv4 has 32 bit, that means 4 byte. So each one is A bit, A bit, A bit, A bit. So A bit means first number is 0 to 255. Okay, second number is also 0 to 255. Okay, this 0 to 255, 0 to 255. So totally is 32 bit. So in a way, totally you have 32 bits. So this IP address totally you can go to 2 to the power 32 is equivalent to 10 to the power 3. Actually, let me see. 3. Yeah, okay, actually 3 times 3, actually 9, okay. Times 4. So actually it's actually totally providing 4 giga IP addresses. Okay, it's actually 4 times 10 to the power 9. That's actually equivalent to 2 to the power 32 number of addresses by the 32 bit. That's the total number of addresses that you can achieve. So in the old days, IPv4 is enough, but now IPv4 is not enough because there are too many computers. Well, each one will use a IP address. So IP address start to not enough. Okay, so we'll talk about IPv6 now.
8 bits for each part of the address. The earlier numbers usually identify the country and regional network of the device. Then come the subnetworks, and then finally the address of the specific device. This version of IP addressing is called IPv4. It was designed in 1973 and widely adopted in the early 80s and provides for more than 4 billion unique addresses for devices connecting to the internet. But the internet has turned out to be much more popular than even Ben Cerf imagined, and 4 billion unique addresses won't be enough. We're now in the middle of a multi-year transition to a longer IP address format called IPv6, which uses 128 bits per address and provides over 340 undecillion unique addresses.
Okay, so this one,
That's more than enough for every.
this one is 2 to the power 128. So divided by 2 to the power 32, it is 2 to the power 96 times more spaces. Is okay? This many times. So many more addresses will be available using the 7 byte structure. 7 byte, each byte is 8 bit. Okay, that become 128 bit. No, let me see. It's not 7. 8 bit. 128 bit. Something's wrong. Okay.
Grain of sand on Earth to have its own IP address.
Most users never see or care about internet addresses. A system called the domain name system, or DNS, associates names like www.example.com with the corresponding addresses. Your computer uses the DNS to look up domain names and get the associated IP address, which is used to connect your computer to the destination on the internet.
And it goes a little something like this.
Hey, hi there. I want to go to www.code.org.
Yeah, I don't know the IP address for that domain. Let me ask around. Hey, they know how to get to code.org?
Yeah, I got it right here. It's 174.129.14.120.
Oh, okay, great, thanks. Yeah, I'm gonna write that down and save it for later in case I need it. Hey, here's that address you want.
Okay, so when you don't know what is yahoo.com IP address, you will use as your ISP, and your ISP don't know, you will actually ask some other computer. So this different other computer, we call it domain name service. They will provide you a name when there is somebody who know. Is that okay?
Yeah.
So how do we design a system for billions of devices to find any one of billions of different websites? There is no way one DNS server can handle all the requests from all devices. The answer is that DNS servers are connected in a distributed hierarchy and are divided into zones, splitting up responsibility for the major domains, such as .org, .com, .net, etc. DNS was originally created to be an open and public communication protocol for government and educational institutions. Because of its openness, DNS is susceptible to cyber attacks. An example attack is DNS spoofing. That's when a hacker taps into a DNS server and changes it to match a domain name with the wrong IP address. This lets the attacker send people to an imposter website. If this happens to you, you are vulnerable for more problems because you are using that fake website as if it is real. The internet.
Okay, so giving you the wrong address, that's called the DNS spoofing. Okay, spoofing. That's the first thing you need to remember.
It's huge and getting bigger every day. But the domain name system and internet protocol are designed to scale, no matter how much the internet grows.
Okay, this is a domain name service. Now let's try to look at another things. Okay, let's look at how DNS work.
In the world of networking, computers don't go by names like humans do. They go by numbers, because that's how computers and other similar devices talk and identify with each other over a network, which is by using numbers such as IP addresses. Humans, on the other hand, are accustomed to using names instead of numbers. Whether it's talking directly to another person or identifying a country, place, or thing, humans identify with names instead of numbers. So in order to bridge the communication gap between computers and humans and make the communication a lot easier, networking engineers developed DNS. And DNS stands for Domain Name System. And DNS resolves names to numbers. To be more specific, it resolves domain names to IP addresses. So if you type in a web address in your web browser, DNS will resolve the name to a number because the only thing computers know are numbers. So for example, if you wanted to go to a certain website, you would open up your web browser and type in the domain name of that website. So for example, let's use yahoo.com. Now, technically, you really don't have to type in yahoo.com to retrieve the Yahoo web page. You can just type in the IP address instead if you already knew what the IP address was. But since we are not accustomed to memorizing and dealing with numbers, especially when there are millions of websites on the internet, we can just type in the domain name instead and let DNS convert it to an IP address for us. So back to our example, when you type in yahoo.com in your web browser, the DNS server will search through its database to find a matching IP address for that domain name. And when it finds it, it will resolve that domain name to the IP address of the Yahoo website. And once that is done, then your computer is able to communicate with the Yahoo web server and retrieve the web page. So DNS basically works like a phone book. When you want to find a number, you don't look up the number first. You look up the name first, then it will give you the number. So to break this down into further detail, let's examine the steps that DNS takes. So when you type in yahoo.com in your web browser, and if your web browser or operating system can't find the IP address in its own cache memory, it will send a query to the next level to what is called the resolver server.
Okay, number one, what is cache memory? He said that you look at the cache memory, but if cache memory doesn't have it, you go to the ISP. Then what is the cache memory then? Hello?
It stores like copies of data
Hmm?
for
The cache memory actually is a buffer that is stored in your browser. So your browser, when you browse yahoo.com, then browser will remember what the IP address is. So you next time you browse Facebook, and you will remember the Facebook's IP address as well. So then you don't need to ask anybody else, because you do not do that's just like your phone book. You already write down your good friends' numbers, so you don't need to ask that. Search internet to find out somebody's phone number. You don't need that. Your phone book already has it. Is that okay? Now, if you don't have it, then you need to go to as the domain name service resolver. Resolver is the ISP. That's
The
actually
resolver server is
AT&T.
basically your ISP or internet service provider. So when the resolver receives the query, it will check its own cache memory to find an IP address for yahoo.com. And if it can't find it, it will send the query to the next level, which is the root server. The root servers are the top or the root of the
Okay, so
DNS
now if ISP cannot find you, go to the root server. Root server is .org has a root server. .edu has a root server. .com has a root server. So you say yahoo.com, you will go to the root server of the .com. That's the root server. Is that okay?
yeah.
So how many root server in the whole world? How many? There are only about 13, 12 or 13 of them. Okay, not many, because not many .com.
hierarchy. There are 13
13, you
sets
see.
of these root servers,
Is that okay?
and they are strategically placed around the world, and they are operated by 12 different organizations. And each set.
So one is .edu, one is .com, one is .org, or another one is .zbs. You know that? Is that okay?
Yeah.
Those are the top. And then if root server doesn't has it, you go down to the lower level.
Root servers has their own unique IP address. So when the root server receives a query for the IP address for yahoo.com, the root server is not going to know what the IP address is, but the root server does know where to send the resolver to help it find the IP address. So the root server will direct the resolver to the TLD or top level domain server for the .com domain. So the resolver will now ask the TLD server for the IP address for yahoo.com. The top-level domain server stores the address information for top-level domains, such as .com, .net, .org, and so on. This particular TLD server manages the .com domain, which yahoo.com is a part of. So when the TLD server receives a query for the IP address for yahoo.com, the TLD server is not going to know what the IP address is for yahoo.com. So the TLD will direct the resolver to the next and final level, which are the authoritative name servers. So once again, the resolver will now ask the authoritative name server for the IP address for yahoo.com. The authoritative name server or servers are responsible for knowing everything about the domain, which includes the IP address. They are the final authority. So when the authoritative name server receives the query from the resolver, the name server will respond with the IP address for yahoo.com. And finally, the resolver will tell your computer the IP address for yahoo.com, and then your computer can now retrieve the Yahoo web page. It's important to note that once the resolver receives the IP address, it will store it in its cache memory in case it receives another query for yahoo.com, so it doesn't have to go through all those steps again.
Okay, is that clear enough?
Yeah.
Okay. Okay, this one, let's look at this HTTP and HTML.
I'm Jacqueline Lawrence, and I'm a program manager on the Xbox One engineering team. One of our biggest features is called Xbox Live. It's an online service that connects gamers from all around the world, and we rely on the internet to make that happen. This is no easy task, and there are a lot of things happening behind the scenes. The internet is totally changing how people interact and connect. But how does it work? How do the computers all across the world actually communicate with each other? Let's look at web browsing. First, you open a web browser. It's the app you use to access the web pages. Next, you type in the web address, or URL, which stands for Uniform Resource Locator, of the website you want to visit, like tumblr.com.
Hi, I'm David Karp, the founder of Tumblr, and we're here today to talk about how those web browsers we use every day actually work. So you've probably wondered what actually happens when you type an address into your web browser and then hit enter. And it really is about as crazy as you can imagine. So in that moment, your computer starts talking to another computer called a server that's usually thousands of miles away. And in milliseconds, your computer asks that server for a website, and that server starts to talk back to your computer in a language called HTTP. And HTTP stands for Hypertext Transfer Protocol. And you can kind of think of it as the language that one computer uses to ask another computer for a document. And it's actually really pretty straightforward. If you were to intercept the conversation between your computer and a web server on the internet, it's mainly made up of something called GET requests. And those are really very simply the word GET and then the name of the document that you're requesting. So if you're trying to log into Tumblr and load our login page, all you're doing is sending a GET request to Tumblr's server that says get/login. And that tells Tumblr server that you want all of the HTML code for the Tumblr login page. So HTML stands for Hypertext Markup Language. And you can think of that as the language that you use to tell a web browser how to make a page look. So if you think about something like Wikipedia, which is really just a big, simple document, and HTML is the language that you use to make that title big and bold, to make the font the right font, to link certain text to certain other pages, to make some text bold, to make some text italic, to put an image in the middle of the page, to align the image to the right, to align the image to the left.
The text of a web page is included directly in the HTML, but other parts, images or videos, are separate files with their own URLs that need to be requested. The browser sends separate HTTP requests for each of these and displays them as they arrive. If a web page has a lot of different images, each of them causes a separate HTTP request, and the page loads slower. Now, sometimes when you browse the web, you're not just requesting pages with GET requests. Sometimes you send information, like when you fill out a form or type a search query. Your browser sends this information in plain text to the web server using an HTTP post request.
So let's say you log into Tumblr. Well, the first thing you do is you make a post request. That is a post to Tumblr's login page that has some data attached to it. It has your email address. It has your password. That goes to Tumblr server. Tumblr server figures out that, okay, you're David. It sends a web page back to your browser that says, success, logged in as David. But along with that web page, it also attaches a little bit of invisible cookie data that your browser sees and knows to save. And that's really important because it's really the only way that a website can remember who you are. And all that cookie data really is an ID card for Tumblr. It's a number that identifies you as David. And your web browser holds on to that number. And then the next time you refresh Tumblr, the next time you go to tumblr.com, your web browser knows to automatically attach that ID number with the request that it sends over to Tumblr server. So now Tumblr server sees the request coming from your browser, sees the ID number, and knows, okay, this is a request from David.
Now, the internet is completely open. All of its connections are shared, and information is sent in plain text. This makes it possible for hackers to snoop on any personal information that you send over the internet. But safe websites prevent this by asking your web browser to communicate on a secure channel using something called Secure Sockets Layer and its successor, Transport Layer Security. You can think of SSL and TLS as a layer of security wrapped around your communications.
Okay, so when you have http://www.yahoo.com, this one is a normal website. And then if you want it to be secure, then you will do this secure SSL. Then you need to use HTTPS with the S. That's a secure website. And then use a www. So let's try it, okay? We will go back to the video later. Let's let you try this one. So let's come here, okay? And then you can try HTTP www.yahoo.com. So this one is non-safe, not SL website. So let's try HTTPS and then ctbank.com with the S right here. I do type in the S right here. So that is a secure access. So you will use the SSL to call it. Okay, so these are different secure level. So these two, whether you use a secure website or non-secure website, is up to. I'm sorry, which one I'm using? Wait, where it is? I kind of lost it. I think we finished this one. We are on the, let's see, is that this one? Okay, I'll find it. Okay, I'll find it. Maybe here. Okay, it's actually right here. Okay, so you will be using secure or non-secure, transport TSL or SSL. Okay, and then that require cookie. Okay, they require cookie to set up a safe or unsafe session.
Protect them from snooping or tampering. SSL and TLS are active when you see the little box that appears in your browser address bar next to the HTTPS. The HTTPS protocols ensure that your HTTP requests are secure.
So this is S with a secure, okay.
When the website asks your browser to engage in a secure connection, it first provides a digital certificate. which is like an official ID card, proving that it's the website it claims to be. Digital certificates are published by certificate authorities, which are trusted entities that verify the
this one
identities of
is
websites
issued by
and issue certificates.
by certificate authority. What does this mean? This means that I have a computer and then I want to log into Citibank. So Citibank doesn't know me. I don't know Citibank. So maybe Citibank is a fake website, and maybe my computer is a fake person. Each other don't trust itself. So there's a third party. This third party is called certificate authority. So you talk to here using HTTPS, and then Citibank would check with the certificate authority, saying, oh, is this guy real person or not? Okay, it is. And then I also check with the authority saying, is a Citibank is a regular website or is it a fake website? And either way, they say, yes, Citibank is a website and this person is real. Okay, because of that, then they will give you a digital certificate. We call it cookie. So this cookie is sent to Citibank and sent to me. So we all know that, the Citibank that I'm logging in is real using the digital certificate. And that is given by the authority. It's a third-party website. Is that okay so far? At the end, it's okay so far?
Yeah.
It's another organization, okay?
Just like a government can issue IDs or passports. Now, if a website tries to start a secure connection without a properly issued digital certificate, your browser will warn you. That's the basics of web browsing.
Okay, so when there is no cookie, then you cannot log into the website because it's a dangerous website, okay?
The internet we see day to day. To summarize, HTTP and DNS manage the sending and receiving of HTML, media files, or anything on the web. What makes this possible under the hood are TCP/IP and router networks that break down and transport information in small packets. Those packets themselves are made up of binary, sequences of ones and zeros that are physically sent through electric wires, fiber optic cables, and wireless networks.
Okay, so this video talk about this HTML DNS. Now we are going to look at this TCP and routing, okay? And finally would be the wire, okay? So that's actually one by one, do it one by one, okay?
Fortunately, once you've learned how one layer of the internet works, you can rely on it without remembering all the details. And we can trust that all those layers will work together to successfully deliver information.
So all the layer is the 7 layer we talk about so far, okay? We talk about 7 layer architecture. So those are application layer, presentation layer, session layer, transport layer, network layer, and then data link layer, and then physical layer. Okay, those are 7 layers. You need to remember all of them. Okay, you need to remember all of them.
And with reliability.
Okay, this one is done. Let's try another one. Let's try the second one. Second one he talked about. Okay, second one he talked about is first one is HTTP and DNS. Second one is called routing and the packet. Okay. So routing, packet, and reliability. This one.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. How is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify.
Okay, reliability means that you want to connect with Spotify. Okay, but these different route may break down somewhere. Okay, so but you still need to connect with the Spotify. So how these things can be connected safely? There are 3 redundancy you can do. Number 1, hardware redundancy. Okay, second one, software redundancy. Third one, coding redundancy or information redundancy. Okay, let's look at first one, hardware redundancy. Hardware redundancy means that originally you are here and Spotify is here, so you actually have one route you can go through here. But one route, if we break down, that you cannot go through. So that's actually build thousands of different routes. So when this breakdown, I still have another route I can go through. So with more routing, I should be able to go to the destination, maybe a little bit later, but you will arrive. This is called hardware redundancy. Is okay?
Yeah.
So let's assume that you are doing trading with the you buy stock. You're doing trading with like Wall Street. So Wall Street has a server right there. Okay, and everybody log into the Wall server, and then to buy stock and sell stock. But if someday this computer down, then what? Your money is lost. So we cannot allow it to happen. So what happens is that Wall Street usually is not one machine running. Actually, they will have two machines running together and doing the same thing. Okay, so say Wall Street, maybe E-Trade, or maybe someone else, they have two computers. They have two computers working together, but if one down, the other still be working. They back up each other. Is that okay so far?
Yeah.
This we call it hardware redundancy. Hardware redundancy is providing more routing or more computer to help it. Okay, it's called hardware redundancy. Now, second one is software redundancy. Software redundancy means that I do have one route. I send data to the other side and receive some data to the other side, but somehow one of the data is lost. So I keep here and then I start to use my stopwatch and I wait for 5 minutes, and 5 minutes later, what I wanted still haven't come. Then I will tell my other party, say Spotify.com, saying, hey, your package is lost, send it again, and then Spotify will send again. This we call it software redundancy. It's retransmit data. Maybe same network hardware, one same hardware, but now I do software, I resend it. This is called software redundancy. Is that okay?
Yeah.
Third way to do reliability is you have a computer, okay? Spotify have a computer. You do set up a lens. You do just request one data, but this one data we have extra bits to check if the original data is correct or not. So when the data arrive at the computer, I'll check if the data is correct data or not based on the check code I sent over. So there's some check code you can help to check verify your data. This extra code we call it information redundancy. So you can use the software using extra code or using extra hardware to do it. So redundancy usually is you provide extra resource, maybe hardware, maybe software, maybe more coding to help you to handle the things more reliably. Okay, that's cool. So remember the 3 different kind of redundancy. Okay, I will go through the video and we'll discuss later. Okay.
Seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there's no guarantee that every wire in a computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet, a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it will be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the internet protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. You need to be 100% sure all the data will be delivered so the song plays perfectly. Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgements of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices or routers along the internet help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
Okay, any questions so far?
No.
This is about routing and packaging, okay? This next one is do wire and cable. Okay, this one. The lowest level in mind.
My name is Tess Winlock. I'm a software engineer at Google. Here's a question. How does a picture, text message, or email get sent from one place to another? It isn't magic. It's the internet, a tangible physical system that was made to move information. The internet is a lot like a postal service, but the physical stuff that gets sent is a little bit different. Instead of like boxes and envelopes, the internet ships binary information. Information is made of bits. A bit can be described as any pair of opposites, on or off, yes or no. We typically use a 1 meaning on or a 0 meaning off. Because a bit has two possible states, we call it binary code. 8 bits strung together makes 1 byte. 1,000 bytes all together is a kilobyte. 1,000 kilobytes is a megabyte. A song is typically encoded using about 3 to 4 megabytes. It doesn't matter if it's a picture, a video, or a song, everything on the internet is represented and sent around as bits. These are the atoms of information. But it's not like we're physically sending ones and zeros from one place to another, one person to another. So what is the physical stuff that actually gets sent over the wires and the airwaves? Well, let's look at a small example here of how humans can physically communicate to send a single bit of information from one place to another. So say that we could turn on a light for a 1 or off for a 0, or use beeps or similar sort of things like Morse code. These methods work, but they're really slow, error-prone, and totally dependent upon humans. What we really need is a machine. So throughout history, we built many systems that can actually send this binary information through different types of physical mediums. Today, we physically send bits by electricity, light, and radio waves. To send a bit by electricity, imagine that you have 2 light bulbs connected by a copper wire. If one device operator turns on the electricity, then the light bulb lights up. No electricity, no light. If the operators on both ends agree that light on means 1 and light off means 0, then we have a system for sending bits of information from one person to another using electricity. But we have a problem. Let's say that we want to send 5 zeros in a row. Well, how can you do that in such a way that either person can actually count the number of zeros? Well, the solution is to introduce a clock or a timer. The operators can agree that the sender will send 1 bit per second, and the receiver will sit down and record every single second and see what's on the line. To send 5 zeros in a row, you just turn off the light. Wait 5 seconds, the person on the other end of the line will write down all 5 seconds, say 0, 0, 0, and for ones, do the opposite, turn on the light. Obviously, we'd like to send things a little bit faster than 1 bit per second, so we need to increase our bandwidth, the maximum transmission capacity of a device. Bandwidth is measured by bit rate, which is the number of bits that we can actually send over a given period of time, usually measured in seconds.
Okay, bandwidth is a little bit like
speed is the latency, or the amount of time.
Bandwidth is like a little bit like you have a pipe, and then how much water can go through per second. So maybe 2 liters per second. That's the maximum amount of the pipe that can carry. But that doesn't mean that the water goes through, it will be 2 liters per second. Maybe the water only half of it. Okay, only half of it, and then it will be 1 liter per second. So the 2 liters per second is the capacity, the maximum that you can carry. Okay, you cannot go over the maximum.
Takes for 1 bit to travel from one place to another, from the source to the requesting device. In our human analogy, 1 bit per second was pretty fast, but kind of hard for a human to keep up with. So let's say that you want to actually download a 3 megabyte song in like 3 seconds. At 8 million bits per megabyte, that means a bit rate of about 8 million bits per second. Obviously, humans can't send or receive 8 million bits per second, but a machine can do that just fine. But now there's also a question of what sort of cable to send these messages over and how far the signals can go. With an Ethernet wire, the kind that you find in your home or office or school, you see really measurable signal loss over just a few hundred feet. So if we really want this internet thing to work over the entire world, we need a different way of sending this information really long distances. I mean, like across an ocean. So what else can we use? Well, what do we know that moves a lot faster than just like electricity through a wire? Well, light. We can actually send bits as light beams from one place to another using a fiber optic cable. A fiber optic cable is a thread of glass engineered to reflect light. When you send a beam of light down the cable, light bounces up and down the length of the cable until it is received on the other end. Depending on the bounce angle, we can actually send multiple bits simultaneously, all of them traveling at the speed of light. So fiber is really, really fast. But more importantly, the signal doesn't really degrade over long distances. This is how you can go hundreds of miles without signal loss. This is why we use fiber optic cables across the ocean floors to connect one continent to another. In 2008, there was a cable that was actually cut near Alexandria, Egypt, which really interrupted the internet for most of the Middle East and India. So we take this internet thing for granted. It's really a pretty fragile physical system. And fiber is awesome, but it's also really expensive and hard to work with. For most purposes, you're going to find copper cable. But how do we move things without wires? How do we send things wirelessly? Wireless bit sending machines typically use a radio signal to send bits from one place to another. The machines have to actually translate the ones and zeros into radio waves of different frequencies. The receiving machines reverse the process and convert it back into binary on your computer. So wireless has made our internet mobile, but a radio signal doesn't travel all that far before it completely gets garbled. This is why you can't really pick up a Los Angeles radio station in Chicago. As great as wireless is, today it still relies on the wired internet. If you're in a coffee shop using Wi-Fi, then the bits get sent through this wireless router and then are transferred to the physical wire to travel the really long distances of the internet. The physical method for sending bits may change in the future, whether it's lasers sent between satellites or radio waves from balloons or drones, but the underlying binary representation of information and the protocols for sending that information and receiving that information have pretty much stayed the same. Everything on the internet, whether it's words, emails, images, cat videos, puppy videos, all come down to these ones and zeros being delivered by electronic pulses, light beams, radio waves, and, lots and lots of lots.
Okay, so there are three ways to do communication. One is using wire. One is using fiber. So fiber is light, okay, light. And then another one is using radio frequency. Okay, three different types. Copper wire, okay, fiber that's using light. So this one using electricity, okay. And then this one using EM wave, okay. This actually are different devices. Okay, so we pretty much finished the top and down level from the HTML, the top level, to the middle level, the networking and routing, and then to the lower level, to physics. Now let's look at two more things. And that next one is the problem the internet would have. So let's look at also the code.out video. Okay, code.out video is more straightforward. Let's see. Okay, let's look at this. How to not get hacked. Let's look at this cyber crime and security.
Hi, my name is Jenny Martin, and I'm the Director of Cybersecurity Investigations at Symantec. Today, cybercrime causes huge problems for society, personally, financially, and even in matters of national security. Just in the last few years, hundreds of millions of credit card numbers have been stolen. Tens of millions of social security numbers and healthcare records were compromised. Even nuclear centrifuges have been hacked, and unmanned aerial drones have been hijacked. This is all done by exploiting vulnerabilities in hardware and software, or more often by taking advantage of unintentional decisions made by the people using the software. People committing these cybercrimes don't fit a single profile or motivation. It could be anyone from an international terrorist to a teenager competing for bragging rights. Today, the largest countries not only have a regular army, but also have a well-armed cyber army. In fact, the next world war may not be fought with traditional weapons, but with computers used to shut down national water supplies, energy grids, and transportation systems.
Hi, my name is Parisa, and I'm Google's security princess. I've worked on a lot of different Google products in a lot of different ways to try and make our software as secure as possible. Now let's take a look at how cybercrime works under the hood. We'll learn about software viruses, denial of service attacks, and phishing scams. In biology and life, a virus is an organism that is spread by coughing, sneezing, or physical contact. Viruses work by infecting cells, injecting their genetic material, and using those cells to replicate. They can make people really sick and then spread to other people. A computer virus works a bit similarly. A virus is an executable program that gets installed, usually unintentionally, and harms a user and their computer. It's also possible for a virus to spread itself to other computers. Now, how does a virus get on your computer in the first place? There are a couple ways an attacker can infect someone's computer. They might lure a victim into installing a program with deception about the program's purpose. So, for example, a lot of viruses are disguised as security updates. It's also possible that the software on your computer has a vulnerability. So an attacker can install itself without even needing explicit permission. Once a virus is on your computer, it can steal or delete any of your files, control other programs, or even allow someone else to remotely control your computer. Using computer viruses, hackers can take over millions of computers worldwide, and then use them as a VPN, otherwise known as a botnet, to attack and take down websites. This kind of attack is called a distributed denial of service. A denial of service is when hackers overwhelm a website with too many requests. We call it a distributed denial of service when the attack comes from many computers all at once. Most websites are ready to respond to millions of requests a day, but if you hit them with billions or trillions of requests coming from different places, the computers are overloaded and stop responding. Another trick used by cyber criminals is to send large amounts of spam email in an attempt to trick people into sharing sensitive personal information. This is called a phishing scam. A phishing scam is when you get what seems like a trustworthy email asking you to log into your account, but clicking the email takes you to a fake website. If you log in anyway, you've been tricked into giving your password away. Hackers can then use your login credentials to access your real accounts, to steal information, or maybe even to steal your money. Fortunately, there are many companies, laws, and government organizations working to make the internet safer, but these efforts are not enough. You may think when a computer system gets hacked, the problem is the security design or the software. 90% of the time a system gets hacked, however, it's not because of a security bug, but because of a simple mistake made by a human. It turns out there are steps we can all take to protect ourselves. Often, your actions not only impact the security of your own data and computer, but the security of everyone at your school, workplace, and home. With billions or trillions of dollars at stake, cyber criminals get smarter each year, and we all need to keep up.
Okay. So today we go through what is internet and then 7 layers of the internet protocols, and then each of the layer what they will do. Okay, and also we look into the redundancy and reliability, and then we look into the wire, which kind of wire transmit, and how fast it would do and how much energy it will lost. Okay. And then last, we look into the phishing. Phishing is to bite, to trick you, to send your personal information, or deny distributed denial of service. That's actually try to jam your website, so your website cannot operate properly. Or you may have a virus that may cause your computer to shut down. Okay, so these are different problems with the internet. So we talk about what is the internet, how to build an internet, and then how internet operate, and also what's the problem that actually impacting the internet right now. Okay. Any questions so far?
No.
Okay, so I don't know whether this help you for reviewing your test tomorrow or not, but I'm trying my best. Okay. Any question? No. If no, that's it for today. Okay. Wish you good luck tomorrow for the test. Okay. Good night, then. Bye bye.